Hello students, my name is Shashank Shekhar. So today is the 10th lecture of the chapter Haloalkane and Haloarene. So we have covered up till haloarene preparation and all. So today we will see some commercial products of this haloalkanes and haloarenes which is used in our day-to-day life. So if you look at the syllabus here, so basically we have covered up till this part, that is haloarenes and directive influence of the halogen in monosubstituted compound. Now today we will be seeing the uses and environmental effect of some of the commercially available products, that is dichloromethane, trichloromethane, tetrachloromethane, iodoform, freons, DDT, and their preparation. So we'll see their preparations also. So if you look at today's topic, so first we will see the reaction with metals. So I am just here giving a comparison between the reaction of metal. So two cases can arise. So we'll see it. After that, we'll see preparation and properties of different commercially available halogen containing compound like dichloromethane, chloroform, carbon tetrachloride, iodoform, freons, DDT. And since this preparation of DDT is complex, so I put up a different slide for it along with its mechanism. Before starting our today's topic, let us look at some examples. So I have put up some disubstituted haloarene. So they are disubstituted in the way you can see that two substituents are present. So let us look at the reaction. Means what product could we expect during the electrophilic aromatic substitution of this disubstituted benzene. So these examples are very important from the JEE point of view, as you will get this kind of examples only where you have to decide and you can say you have to basically compare the competence, that which one will be affecting more your benzene ring. So to understand that, you must have a clear idea of what a halogen does to a bromine ring. Now I have told you yesterday also that this halogen is having more inductive effect, or you can say more minus I effect, rather than its resonance effect, or you can say it is more pronounced. Due to this reason, halogen is overall kind of a deactivating group. So it deactivates the benzene, and the electron cloud is now present in less amount, or you can say it's present in less magnitude as compared to our benzene electron cloud, because of the greater inductive effect or greater electronegativity of halogen compound. So keeping this concept in mind, let us look at some questions here. So here the two substituents are OCH3 and Br. So if you have remembered the previous class, then I have put up a general idea to decide that whether it is ortho-para directing or that is meta directing. So if a compound looks like this, or whether it is having a triple bond, in both these cases it will become meta directing because it will go like this. But if a lone pair is present, example this one, it will donate this lone pair and it will become ortho-para directing. So if you see both of these group, they both are same as this, that they both are ortho-para directing. Now if you look at Br, first of all we look at Br here. So where are its ortho and para position? This are ortho and this is para. Now if you look at OCH3, the ortho and para will be, so these two are ortho and this one is para. So they both are kind of doing the electrophilic, or you can say electronically favoring the electrophilic aromatic substitution at these 3 points. This is only the electronic effect, or you can say this is only the electronic output that can be expected, because only electron density has been increased on these 3 points due to the plus R effect or the plus M effect, because the lone pair will resonate and it will make this ring ortho-para enhanced. Similarly, this Br lone pair also will do the same. Now 4 products are possible. How? So it can be substituted here, here, here and here. So talking about this one, so since this one is not a kind of being this one is kind of not being activated by the either OCH3 or Br. Therefore, this one is not certainly the product. Now we are left with three possibilities here, here, and here. Now this one is also outruled. Why? Because if you put NO2 here, it will be too hindered. Three substituents consecutively will be a too hindered product. Okay, for that reason, it is not formed. So one is electronically not favorable, and another one is sterically not favorable. Now we are left with two of these. So only two of these will be formed. This one means at this position and at this position. You can see here. So two kind of substituents occur, A and B. So the same thing is written here, that OCH3 and OBr are both ortho-para-dialectic, ruling out the D position. Now product C is disfavored due to steric hindrance. Therefore the correct answer are A and B. Note the additive effect of substituent. So this is the first example of disubstituted. Let us take one more example. So here we have taken NHCOCH3 and chlorine. So if you look at first the nature of both the substituents, so they both look like ortho-para-dialectic, as they both have lone pair and there is no double bond here. And since there is no consecutive element, so there will be no chance of your meta direction. So if you see the ortho-para position, so this NH will have ortho and ortho here, and here para. Similarly, this chlorine will have one ortho here, and one para. So if I draw it again, it will look like this. So let me draw it on a more better place. So whatever may be the group. Okay, let me consider it. So both of these have different products. So this one will be, so if I talk about NH, so the relative ortho and para positions are, so this is first ortho position, second ortho position, and this is a para position. If you move to Br, then the possible ortho positions are this, and this is para. So if I mark it here also, this is ortho. Sorry, this one is not ortho. This one will be ortho. So this will be ortho and this will be ortho. Now they both are directing at different spots. Means they are just complementary to each other. Here you can look it very clearly. They are both complementary to each other. Now which one will decide this incoming electrophile? So first of all, this position is already occupied, so it will be not substituted. Same for this NH. Since this position is already occupied, it will be not substituted. So we are left with this 1, 2, 3, and 4 options. Now the concept that plays the role here is that you know it very well that Br is kind of, we can say, both ring deactivating, and the bond between Br and carbon is not that much similar in aspect of this energy. So this bromine is of much higher atomic number. Therefore, it's occupied, you can say the highest occupied molecular orbital or HOMO is present at a very high energy as compared to the orbital that will accept the electron, that is the lowest unoccupied molecular orbital of your, say, this carbon. So due to this energy difference first, and second, due to the greater electronegativity of a bromine, it will be donating comparatively less electron than NH3. Now, due to these two reasons, the energy difference between carbon and bromine and the electronegativity of bromine, it will not be able to donate its electron that much efficiently. Therefore, this NH will play a better role. Okay, this NH will play a better role in deciding your product. Therefore, we will only consider the ortho and para position of NH. Now, since one is already occupied, we are left with two. So this one and this one. So the product will be accordingly, both of this will be occupied. So it's the same thing written here. The N-acetyl and chlorine are both ortho-para directors, but disagree on where substituent should occur. Means they both are ortho-para directing, but their directing positions are different. Now we know that N-acetyl is a stronger activating group, so it gets the decide. So as I mentioned earlier, since Cl is kind of deactivating, so it will not be the deciding one, but NH will be the deciding one, that where your substituent will go or where your electrophile will go. So this is the last example. So here what we have used, this iodine and SO3H. Now students, comparing both of this, so one will be meta directing and one will be ortho directing. How? So for that we have to expand the SO3H structure. So SO3H will look like this. Now this lone pair will be now, sorry, this pi bond will be now moved here. So I mentioned earlier, so if you have kind of this configuration or either this configuration, in both these cases we will see meta substituting. Okay, but students, one more thing, you will ask that suppose this A here has both lone pair plus this bond pair, then in that case also it will be meta directing rather than ortho para directing. There are much more things to decide, but for now assume it like this only, that although this A will contain your lone pair, but also it will be meta directing. So this is kind of deactivating the ring. Now compared to this I, it is activating the ring, or it is much more greater activator than your SO3H group. Now due to this reason, the final product will be decided by your I. So which is the ortho and para with respect to iodine? This is ortho, and this one is para. So our substituent will go here and here. The same thing has been written here. We are giving Br here and Br here. Now you will ask that, okay, you have disagreed with this, say you have told us earlier that we have steric hindrance, so we cannot put three substituents consecutively, but here you have done the same. So look here students, in the earlier part we have seen that the substituent which was being substituted in middle was kind of not linear one. I would not say linear one, it was not a linear one. Yeah, it was not a linear one. See, NO2 looks like this. It is trigonal planar. So this bond will rotate. Since it is single bond, there is the energy barrier is very less, so it will rotate. Now it will clash with the side substituent. But in this case, we have iodine. We do not have to think of the hindrance. Okay. Due to this reason, we can afford this consecutive substitution. Okay, this is clear. Now this meta, again, meta to I, both of the positions that are meta to I are been disagreed or disfavored because SO3H is not a good activating group than iodine. Okay, this is clear. So these are some of the example of di-substituted electrophilic aromatic substitution. Now we will move to reaction with metals. So both of these reactions I have mentioned earlier also, but now just for a comparison so that you can remember the names accordingly. So if you see the Wurtz-Fittig reaction and the Fittig reaction, then both of these are having the same reagent, that is Na, Na and dry ether. Now what is the difference here in both of these reactions? That we are using two different alkyl in this case. So you can see that here one is Rx and one is phenyl, but here both are phenyl. So Wurtz-Fittig and Fittig have only one difference, is that and the difference is that we take 2 moles of the same halogen containing compound in case of fatigue reaction, and in case of Wurtz fatigue we take 2 different halogen containing compound like this one. Okay, like this one. So here it is written, a mixture of an alkyl halide and an aryl halide gives an alkyl arene. So it is aryl halide, it is alkyl halide, and we are getting an alkyl arene. And when it is treated with sodium in dry ether, it is called Wurtz fatigue reaction. So you can see that they both are coupled. This part and this part are coupled, and we get this one. Now, I would mention one more point here, that this goes through radical mechanism. Okay, this and this both goes through radical mechanism. We will not go into the whole mechanism right now, but remember this thing because it helps in predicting the proper product. Remember this thing, that it goes through radical mechanism. Now the one which will be forming radical easily will be the halogen that will be substituted. Okay, now in case of fatigue reaction we use both the halogen containing compound same, means the alkyl group of both the compounds are same. We have taken 2 moles of it only, and since we have taken the same compound, therefore we will get a kind of symmetrical compound. We we got a symmetrical compound, a diphenyl. So we can make a more general statement here, that fatigue reaction gives us a symmetrical compound as the product, whereas Wurtz fatigue does not give so. Is this clear? And remember the side product also, it is NaX and it is 2NaX. No problem, it has just been divided by multiplied by 2 because we are using the same moles of 2. Here we cannot do the same. Okay, this is clear? Okay, so this one was the reaction with metals. This is just a revision. So today we will start with some of the commercial products, starting with dichloromethane. So dichloromethane is a geminal halogen, dihalogen. What does this mean? It means that both the halogens are on one carbon. So if you see this structure of this CH2Cl2, it will be having both the chlorine on the same carbon, like this. And it is also called methylene chloride. So you should be well aware about these names also, because sometimes in the exams you will be given this name and you may not do the simple questions just because of the unknown nature of the name. And one more name is here, that is methylene dichloride. Now how it can be obtained? It can be obtained from oceanic source, macroalgae, volcanoes and wetlands. Now the majority of methyl dichloride in the environment is due to industrial emission. The chemical formula is this. So why it is very useful? Because it is used as a solvent in food technology. Also it is used in aerosol formation and in ethane foam blowing agent. Now it is used as a solvent as manufacturing of pharmaceutical products, and it is also a degreasing agent. Degreasing means sometimes if you see the bikes, motorbikes and all, they are oiled with grease, or you can say they are lubricated with grease. So to remove that grease we use this dichloromethane. Again it is used in manufacturing of electronic. So you can see that how commercially important this dichloromethane is, and it can be made in the labs also, this CH2Cl2. Okay, so if you simply do this chlorination using your light and all, HNO and all, so you will get your dichloromethane. So by the chlorination of your methane you can get this dichloromethane. Next is trichloromethane. So trichloromethane chloroform is very popular for this. So it is trichloromethane is an organic compound which was initially employed as ideal anesthetic. So anesthetic means it was used to perform surgeries and all. So to make the body parts senseless, or you can say numb, they use this chloroform. You must have seen in pictures also that they take the your chloroform in one of your clothes or cotton cloth, and they just put it on the nose of one who is getting to be kidnapped, and they are just being say unconscious. So you can say that this chloroform is used for that. It was used for that earlier, but later on some harmful side effects was seen due to the use of this anesthetic, and it was later on removed from clinical practices. So it was first prepared in 1831. Its formula is CHCl3. It is just a derivative of your methane in which we have substituted 3 hydrogens with 3 chlorines. Now it is a colorless, sweet smelling, dense liquid produced on a large scale. So it is used as anesthetic, I've told you just now, and is used in dentistry during root canal procedures. The spectrum of pure chloroform is used for the reference or background, and pure cholesterol powder or cholesterol from milk product is dissolved in chloroform and used for FTI analysis. So this FTI analysis is basically a kind of spectrochemical method that is used for identifying a given compound. Chloroform was utilized in the past as an extraction dissolvable for fats, grease, oils, and different items as a laundry spot. Laundry spot means it was used earlier. Suppose you got your clothes dirty due to exposure of your oil or something edibles or like that, then you can use this chloroform because it dissolves all of these fats and grease, oils, and different items. Okay, and you make your clothes clean. It is also used as an indirect food additive in food packaging material for adhesive compound and as component of food contact material. So if you look here, so here is the preparation method of this NaOH, CCl3, CHOH whole twice, and it gives CHCl3. Okay, this is clear. Now we got your HCONA and H2O. So this is the equation that is used for the preparation of this trichloromethane. Next is carbon tetrachloride. So it is a liquid with sweet smell that can be detected at low level. The molecular formula of carbon tetrachloride is CCl4. So this CCl4 is generally used as solvents in organic synthesis, and it is used for manufacturing of refrigerants as cleaning agent and also for fire extinguisher. Medically, it has most potent hepatotoxins, toxic to the liver. It is toxic to the liver and is widely used in scientific research to evaluate hepatoprotective agents. So when this carbon tetrachloride is released into air, it rises in atmosphere and depletes the ozone layer. Okay, it depletes the ozone layer, and depletion of the ozone layer is believed to increase human exposure to ultraviolet rays. You must have heard this point very many times, that due to depletion of this say your ozone layer that is formed of O3, we can get exposed to ultraviolet rays that is being emitted from sun, and it is very harmful to our skin, and this can result in skin cancer, eye disease and disorder, and possible disruption of the immune system also. So this carbon tetrachloride is very harmful for your environment. Next is iodoform. So iodoform is very useful and kind of used in tests. So it is used for testing this aldehyde and ketone if it is present in a given compound or not. So it is called as iodoform test. Okay, so basically it is used for the detection of your acetyl carbonyl, that is CH3CO. So it is basically triiodomethane, which is a crystalline yellow crystalline solid. So it has the formula CHI3. Now it is insoluble in water but soluble in solvents like ethanol, chloroform and iodine. Since it is not that much polar, so it is not soluble in water. Now it is hydrolyzed to give sodium methonomate or sodium formate, that is NaHCONA, that is HCOONA, and when it is treated with aqueous sodium hydroxide solution. So when this triiodomethane is treated with aqueous sodium hydroxide solution, so our CHI3 is treated with sodium hydroxide aqueous solution. It is a kind of hydrolyzing this say our iodoform. Then we get HCOONA. Okay, HCOONA. And some of side products. Iodoform was used earlier as an antiseptic, but the antiseptic properties are due to liberation of free iodine and not due to iodoform itself. So basically it is written that this can be used as antiseptic also, but this nature of this antiseptic properties are not due to this iodoform, but due to the iodine gas that is being liberated from iodoform. Now, due to its objectionable smell, it has been replaced by other formulation containing iodine. Means it is written that it was earlier used as an antiseptic, but due to its odor or due to its smell, we have now different material that is being used for iodine or formulation containing iodine. So this is iodoform. Next is freon. So what is freons? So freons are the chlorofluorocarbons, so CFCs of methane and ethane. And the chlorofluorocarbons refer to the compound having mainly carbon, fluorine, and chlorine. Fluoro, and carbon means chlorine, fluorine, and carbons. Freon is in the brand name for this compound. So freon is basically the brand name for this group of compound coined by DuPont. Okay, they are extremely stable, unreactive, non-toxic, and non-corrosive, and easily liquefiable gas. Now, due to this property only, it is used in refrigerator because it is easily liquefiable. So it is used in refrigerators, and it is manufactured by Schwarz reaction, and they are usually produced for aerosol propellants, refrigerators, and air conditioning purposes. But it is also harmful for your ozone layer. It also depletes your ozone layer. So if it is now prepared by Schwarz reaction. So how it is prepared? So first we take the carbon tetrachloride and treat it with SbF3. So you must have remembered this reaction, that is Schwarz reaction. It is basically an halogen exchange reaction that is used for the preparation of fluorides. So we can use AgF also, or you can use this SbF3 also, or you can use this COF also. Okay. Now it will give you CF2Cl2, that is chlorofluorocarbon. So here we have say exchange halogen 2 times. So first time we exchange for one chlorine with fluorine. Again we exchange second chlorine with fluorine. That is to get our CF2Cl2 plus antimony trichloride. So in this way you can synthesize your freon. Now the next one is DDT. So DDT is very famous commercial product of, or you can say halogen containing compound. So it is basically a colorless, crystalline, tasteless, and almost odorless organochloride that is used for insecticidal. It is used as insecticidal. So it is, this DDT is generally say spread in the homes, or you can say in the society, for removal of insects like mosquitoes and all. So it was first chlorinated. It is first chlorinated organic insecticide that is prepared in 1873. But in 1939, Paul Miller identified the different use of DDT. Paul Miller was awarded the Nobel Prize in Medicine and Physiology in 1948 for this discovery. Now it became popular because of its effectiveness against the mosquito that spread malaria and leaves that carry typhus. But due to the ill effects of DDT, like your chemical instability and fat solubility, so it gets soluble in fat, so it can be harmful if it is exposed to food and all. Okay, because food contains fat and it can be absorbed in this, say, your food, and it can be harmful because it is toxic in nature in some kind. That is why it is affecting the mosquito and all. So it got so due to this reason it got banned in many countries. So if you see here, so this is the structure of DDT. So it is bit typical. So you should remember this. Okay, so this can be asked in the exam. This DDT. If you see, it is a very you can say complicated structure. So we'll see the mechanism that can be used to prepare this DDT. So if you see the chemical equations, it look like this. So first, a chlorobenzene is being treated with Cl3CCHO in presence of H2SO4. Then here we see a electrophilic aromatic substitution again. So it is the first step of electrophilic aromatic substitution. Again, we use a different a second mole of this same chlorobenzene, and again we get a, say, your electrophilic aromatic substitution. So here is the structure of this CCl3CHO. So in place of in presence of H2SO4, what happens? This thing here, this H here. Okay, so if you write it like this, so we have this O. Okay, we have this O. Now the H comes here. due to which a positive charge appears on your oxygen. So this is H, it is coming from H2SO4. Now, since it has a positive charge, to neutralize this, what happens? This bond pair goes on oxygen. Now, this step can occur simultaneously also, that it will attack at the same time. This bonded pair can go on oxygen, and it occurs in this that way only. But to make things more simple, I have done it in two steps. So first, it is protonated and this double bond is shifted on oxygen. Then, due to this reason, we get a positive charge on carbon. Now it can act as an electrophile, and we know this chlorine is also para-directing, and since this group is very bulky, so to avoid a steric hindrance, it does not undergo ortho substitution, and rather than that, it goes para substitution. Now we got this product. Again, this H will leave, and again what happens? Since this thing is in the mixture, this H2SO4 in the mixture, we again add this H on this oxygen. It gets protonated and it leaves. Okay. Now we again got a positive charge here, because after this departs, we get a positive charge on this part. Now we introduce another mole of this chlorobenzene. It attacks here, and again this H is removed, and we got our DDT. So it is same as this, so do not get confused. So we could write it like this. Okay. It is the same structure of DDT which I have seen earlier. Only the way of writing it or the orientation is different. Okay. So I have just rotated and put it here, put it here, and put it here. Okay. So this is the structure of DDT, and in this two electrophilic aromatic substitution step, we can do this. So what can be learned from this mechanism? First of all, we can see that two electrophilic aromatic substitution is being used. Means it happens in two steps, and both of the steps include electrophilic aromatic substitution. And what is the electrophile in first case? In first case, this one is the electrophile. Okay. And in the second case, this one is the electrophile. This whole thing is an electrophile. So for the first step, this one is electrophile. In the second step, this one is electrophile. What is the acid being that is being used, or the catalyst that has been used? It is H2SO4. What is the nucleophile in both of these cases? So both of these cases, we have your chlorobenzene, because this is the one that is giving its electron, or that is attracted towards the positive charge. Now what is this thing called? This is called trichloroacetaldehyde. So I would suggest that you should do this mechanism by yourself also. That would give you a more better idea of how this mechanism goes. Now many possibilities occurs. So many possibilities are possible during this reaction. Suppose we take this one, first step. So we have this as our substrate, or you can say both of these are substrate only. So we have this CCl3 CHO. Now this chlorine, as we know, is also para-directing, so it can go here and here, but due to the steric reason, because this is a large group, it goes here. So two possibilities are there. One is ruled out due to the steric effect. Now once we got this product, okay, we got this product. Sorry. So again, I will let me draw it again. Cl3 CHO CCHO. So we got this thing. Here is our OH, and here is our CCl3. Now what are we doing? We're reacting with this thing that is being formed in the first step. With this thing, that is the second chlorobenzene molecule. Now what are the possibilities? Now this can act as an electrophile. This can too act as electrophile. Okay, both of these can act as an electrophile. Did you get my point? So I'm saying that it can also attack here. Okay, this can also attack here, and this can also attack here. So what's the reason that we got the substitution? Means it acted as a electrophile and it acted as a nucleophile. So what's the reason? Why didn't it attack on this? So what is the reason behind it? Suppose it would have happened like this, that this must have attacked here, and we got a diphenyl substitution. Okay, so this can be attacked on here, and we got a diphenyl product. So what is the reason that this has been attacked by on this? So the reason is very simple. So if you see your catalyst, that is H2SO4, H has been used to protonate this oxygen. But if you have to protonate these things, so it would have been very difficult. Okay, this would have been occurred like this. This would create a positive charge here. Suppose this would have happened, and now this would have attacked here. But the problem here is that in this step, in the first step, that is protonation, first of all, this carbon is less electronegative than oxygen. So hydrogen will of course go on the oxygen. And the second reason is it will destroy its aromaticity. So rather than risking the aromaticity, and since this oxygen is greatly electronegative than this carbon, this acted as a electrophile which gives electron, and this acted as a nucleophile. Okay, this is clear. So today what we mainly discussed is about some commercial products like our dichloromethane and chloroform, carbon tetrachloride, iodoform, and freons and DDT and its preparation. So if I ask you that what are the main points here, so first of all, the commercial product that used your Schwarz reaction to get the product was important. That is the chloroform, CCl2F2, because the reaction was quite obvious there. So it can be asked directly that what is the product, or it may be asked that how you can prepare this chloroform. So you can simply use your Schwarz reaction. Okay, so we use their carbon tetrachloride in the presence of your SBF5. We reacted 2 moles of SBF3 with it, and we got our chloroform. And talking about DDT, you must be well aware about its structure and the mechanism that is used for the preparation of this DDT. So this was all about your haloalkanes and haloarenes. So basically we have seen all the preparation and properties of haloalkanes and haloarenes surrounding this physical and chemical properties both. So with this I would like to end my lecture. We will see some questions in the next class regarding this, that is from both from JEE, NEET and all. Okay, so thank you for today's time.